For this problem, we are asked about how many positive integers n are there such that n is a divisor of at least one of the numbers 10 to the power of 40 and 20 to the power of 30. If this is just a very simple item, like we're just asked about the number of, let's say, positive integers for a specific number, let's just say 10 to the power of 40, we actually can take its prime factorization. We can use the prime factorization of 10. You can actually have it later on. We will show it here. And for prime factors, whatever we say, for example, p sub 1, p sub 2, let's say you have here n and you have here m. The number of divisors is just actually n plus m times n plus m. They are the exponents of your prime factors. If it's just equal to 1. But this time, we have 2 of them. In short, we're going to take the prime factorization of both, and we're going to remove some items which are actually captured by both. This is clearly an example of a principle of inclusion and exclusion. We're going to exclude something from that because there might be some numbers that are counted in both. Okay? So, say for example, 2. 2 is of course a divisor of this. That's very clear because 10 is divisible by 2. Even you raise it to whatever exponent is divisible by 2. At the same time, 2 is also divisible by that. That is why 2 is to be removed, to be excluded from the total count when we add the results of this per exponentiation. But it's not just 2. There are even more than that. So how do we know the answer to this? So first, let's attack this problem. As mentioned, let's try to look for the number of divisors for each. Okay? Because if we talk about the two of them, using the principle of inclusion or exclusion, this is what we call about at least one of the numbers. So it could be in A, it could be in B, or it could be in both. Where we define A as the set of positive integers, or positive divisors. We can use it here. Positive integers. That divides, we can just simply write it, divides 10 to the power of 40. And let's just say A as the set of positive integers that divides, sorry for my handwriting, to 20 to the power of 30. Okay? So with that in mind, our formula is actually the cardinality of A plus the cardinality of B minus the cardinality of their intersection. As mentioned, there are items which can be found in both. So for A, we can use this. Let's take its prime factorization. So let's use it here. I'm going to use another space. So for 10 to the power of 40, let's try to get its prime factorization. But of course, it's very large. Okay? But we know that 10 is actually, we cannot, let's try to make it like this. We know that 10 is actually 2 times 5 raised to the power of 40, right? And by using of power law, that means it's actually 2 to the power of 40 times 5 to the power of 40. Okay. So with that in mind, we know now that our n here, as mentioned, or m, you will have your number of divisors is actually 40 plus 1 times 40 plus 1, because these are now prime factors. It's okay to use it like that. So we multiply 41 by 41. This would be our cardinality of your A. The cardinality of A. The cardinality of A or any set, again, talks about the number of elements in each set. So it depends on how do you define set. Is set accounting as a sequence? Is it a set, a collection, or in this case, set of positive integers or positive divisors? So you depend on how it is defined. So you will have here 1681. Now for our cardinality of B, let's add, or let's have the prime factorization of 20 raised to 30. So this is actually, you can have it 2 times 2 times 5. Or 4 times 5, right? 2 times 2 times 5. Let's just simply use prime factors. Later on, you will just be combining them anyway. So you will have here 2 to the power of 30, 2 to the power of 30, 5 to the power of 30. Again, you can just simply add 2 to the power of 60 using laws of exponents, 5 to the power of 30. So the cardinality of B is actually 60 plus 1 times 30 plus 1. That's 61 times 31. You will get here a result of 1,800 91. These are the number of positive divisors n for 20 to the power of 30. So now that we know both of them, the next time here is, how about their intersection? Because we will be using their intersection. So how do we know the intersection? The intersection is actually when we try to multiply them, right? So multiply, so for example, 10 to the power of 40 times 20. This is for the intersection. So I'm going to separate them, right? And 20 to the power of 30. But then this is very large. How would we identify the number of divisors for these very large items, for we don't know the actual results? Of course, if you're going to multiply them, we know that 10 to the power of 40 is 10. What was that? To the power of 40. 5 to the power of 40. And this time you also have 2 to the power of 60. And 3 to the, 20. That's 20. Yeah. Sorry. My bad. 10. Sorry. 10 to the power. Sorry. My bad. It's actually 5 to the power of 30. It's here. Okay? So how about we know the total for this, or the intersection of both? Okay? The intersection of both is actually the GCF, the greatest common factor between the two. Okay? The greatest common factor between the two, because if the greatest common factor, let's say for example 10 and 8. Okay? 10 and 8. The greatest common factor is actually 2, right? This actually is the intersection, the number of divisors in their intersection. Okay, so you will have to take the GCF. So the GCF of this result, you have 20 to the power of 40 rather, 5 to the power of 40, and then you will have 20 to the power of 60, and then 5 to the power of 30. The GCF for that would be the minimum number. So in this case, for 20, the minimum, you have 20 to the power of 40, right? And for 5, that's 5 to the power of 30. That's the minimum. Now, for this, we will now go get the number or cardinality. So, similar, 40 plus 1, 30 plus 1. Okay? Please don't be confused with that. So, 41 times 31, you will get actually 1,271. So, we are using GCF again to get the intersection, so that we can take the least possible for both numbers. Okay? So with that now, all of them are given. Let's return here. So this is actually again A union B is equal to the cardinality of your A is actually given as 1681. We don't need to use cardinality. 1681 plus the second is 1891, 1891, and then minus the intersection 1271. See, it's the principle of inclusion and exclusion is very easy to answer problems as long as you know the characteristics of the sets. So you have 1681 plus 1891 minus 1271. You'll get here a result of 2301 positive divisors that will divide at least one of the numbers, 10 to the power of 40 and 20 to the power of 30. Again, take note, this 1271, one of that is 2. As mentioned earlier, 2 divides both. Okay, in other examples as well. So we have this as our result for this item, but then again, we're able to understand that using the concept of the set themselves, because we don't know what types of sets we have later on. Previously, we only have set S having integers 1 to 1000, 1 to 500. So we know that we have discrete numbers 1, 2, 3, integers, so on and so forth. This time, our sets are actually containing positive divisors for each of the numbers. So we need to look at how do we identify the number of positive divisors, which is again given by this formula. We might have a similar example to this containing 3 different exponentiations for the next one, so please stay tuned. Thank you very much for watching.